Okay. So in this video, I want to talk about parameter estimation. So the maximum likelihood estimation and method of moments. And I think it's important to first discuss like in what context do we use this. So the idea is like what is the actual process to which we get data? The actual process is we get these random variables x1 and xn. So this is our sample. And like for example, this could be drawn from some Bernoulli theta process. So intuitively, we have like n coin flips here. So basically, you only receive the coin flips. So you receive n coin flips. This is the only thing you see. So you only observe this. This is the only thing you observe. You only observe this. And there is, of course, some actual theta that this data was drawn under. There was. Like if you theta is 0.49, 0.51. There exists a theta that the data was drawn from, and you just don't know the theta. And your goal is saying, given what your context, the only thing you have, which is these samples, what is the best data to choose? So that is what an estimator is. And, of course, there is no specific case, but there are different methods to compute it. So we're going to talk about the two most common ones here, which is the method of moments and maximum likelihood estimation. I'll start with maximum likelihood estimation because it's more common. So basically, maximum likelihood estimation is the intuition here is, well, we have some data D. I'll just define to be this set x1 xn. And let's say drawn from some Bernoulli theta process. And well, intuitively, like imagine if the true theta is 0.5, right? And the idea is, well, a good theta here will be that our data was, like, if theta is 0.5, then our data sequence should have a decent probability, or not necessarily, but for a given draw of, like, if this is our actual, let's say, realizations from some big random variables, x1, xn, capital, so these are, like, lowercase. The idea is that for our data, it makes most sense to choose the theta that would make our data most likely. So that may be a bit confusing, but let's consider like the joint density. Or let's consider, the probability of our data given some theta, right? So again, this is because x1, xn was drawn from theta, and we're going to define this to be the likelihood of theta given x. So now the likelihood function is a function of theta. So like the probability takes in x1 and xn. It takes in our data arguments, conditioned on some theta, because this is what the density receives. But then like the likelihood is saying, given that we receive this, let's make it solely a function of theta, because we don't know theta. And the idea is, well, it's almost like we see the data and we look up to the theta that drew this process and says, we should find that theta that would make our data as likely as possible. So like, just like a sort of a very simple example, if our data was head to head n times, the theta that would make this as likely as possible would be theta is 1, right? Because intuitively, it's like if theta was 0.5, our data would be, this wouldn't be very likely. But if theta was 1, this would occur with probability 1, right? So that's like the intuition. We want to choose that theta that would make our data as mostly as likely possible. We could vary it. So this will be the likelihood of theta given x. And the idea is we want to choose the theta, the maximizer. So we want to choose the theta that maximizes L of theta conditioned on x. And we're going to call this, this will be called theta star MLE. Okay, that's the idea. Yeah. So, but usually, like, maybe I'll just simplify the math a bit here. So that is basically the idea here. And this is very common in machine learning because in machine learning, we just parameterize some neural net or whatever via some parameter vector theta, given some data, and then we'll just find that theta that maximizes the likelihood, right? So maybe I'll go a little bit into the math a little bit more here, just really quickly. So I'll just be a bit more formal here. So, we're given x1 and xn, and these are drawn from some density, fx of some theta, right? So there's some underlying theta to which these x were drawn from. And so what we do is we want to find the theta that maximizes the joint likelihood, the joint density. So we'll define the likelihood of theta given x to be the density of x1 to xn under some theta. And we assume that they're independently drawn. So we assume this is an IID process. So the independence allows us to factorize it as follows. Right? And all these are drawn under the same density. So we could take the product and just say the random variable x, this is the random variable x, take on the value xi, condition on theta. And this is the likelihood of x. And usually we typically take the log. So we'll take the log likelihood. And this will turn into the log of a product. So we'll turn the sum from y equals 1 to n of the log of fx of xi given theta. So that's the idea. This is the idea. Yeah. So that's sort of what we're going to say here. Yeah. And then we basically, yeah. So that's sort of like the simple case. Maybe I'll go over, just for simplicity, the Bernoulli case, just because I think it's pretty simple. So if we're given, just to make it straightforward, so we're given n samples from some Bernoulli theta process. And the question is, what theta should we actually believe that our data came from, is the idea. Right, so we'll define likelihood of theta given x. Again, we said it's the product from y equals 1 to n of the density. Right, so the density of fx of x given some theta, well, simply it's theta to the x times 1 minus theta to the 1 minus x. Right, because if x is 1, so x is in the set 0, 1. If x is 1, we get theta. If x is 0, we get 1 minus theta. So this will be theta to the xi, because we're actually getting our realizations of the random variable, 1 minus theta, 1 minus xi. And this will turn out to be, like, if xi is 1, again, it's theta, the density, the probability is theta. If xi is 0, you get 1 minus theta. So when you multiply a bunch of this, it's just going to be the counts of theta times the counts of 1 minus theta, right? So we'll get the sum of xi's times 1 minus theta times n minus the sum of the xi's. Okay, we haven't done anything crazy here. Now I'll take the log. So this is the likelihood. So we're going to get like the sum of xi, log of theta, plus like n minus sum I xi times log of 1 minus theta. And now we need to find the value of theta. So this is find the value of theta, right? Our goal is to find the theta. So if we have some arbitrary function, call this some function of theta, and this is theta, and we need to find the theta that maximizes the likelihood. That says makes our theta the most likely. Well, we need to take the derivative with respect to theta. So we'll take the partial theta of natural log of likelihood of theta given x. So this will be basically sum I xi over theta plus n minus sum I xi. Well, sorry, I guess we could swap this. Sum I xi minus n of, with the chain rule, right? So it will be the derivative inside, which is negative 1 over 1 minus theta. Over 1 minus theta, we'll set this equal to 0. And I guess we could just do some algebra here. So we'll get like negative sum I xi over theta. Sum I haven't done this in a while, honestly. Wait, I think what might be easier, sorry, I haven't done this in a long time. What's probably the best case? I think it's just like an algebra problem. I probably shouldn't multiply. Probably. Yeah, so let me multiply by 1 minus theta over theta to both sides. So we'll get, if I do that, then I get like basically 1 minus theta. sorry, if I multiply by theta, yeah, so I'm going to multiply by 1 minus theta times theta. Yeah, so I'm going to get 1 minus theta times the sum xi plus sum I xi minus n times theta is 0. So I'm going to get like sum xi, let's say, is equal to sum xi theta minus sum xi theta plus n theta. So we see theta is like sum xi over n, which is x bar, which is what we expect. Yeah, so that's theta MLE, right, is this. Nice, so that's MLE. Another method is called method of moments. Method of moments, I think, is a very beautiful method because it really attacks the idea of the difference between the population and sample, right? So really, that's the key, is it really takes into account, like it basically attacks the difference between the population and it takes into account the difference between the population and the sample. So it takes the population and sample. So again, the population is like the actual random variable, x1 to xn. These are the population that like, it doesn't matter at all. It's some like theoretical versus these are our realizations. So these are our realizations. So this is what we could see. Realizations, like it's the data. It's what we could see. We could see this. And the idea is this population, like if let's say, like let's for simplicity say x1, xn is from some Bernoulli theta. Like, again, we don't know what this theta is, but the idea is like, well, we should intuitively, the moments, right? Because like the moments basically form the, like, you know, MGFs, they sort of uniquely determine it. But the idea is like the expectation of x should match like our empirical version, right? Like clearly this is as n goes to infinity, this is true via LLN, well, a large number. But intuitively, like this is, like this sort of maps, this talks about the truth, right? Like, I guess the idea is like, you know, when we think about some random variable x and we get some realization, like this is specific. When we talk about the expectation, it's saying, it's talking about the actual random variable x. We're not concerned at all about any realization we have. Like this is the expectation x. It's with respect to any possible x we could get. So that's the idea here, is like, we're just going to concern about the true population. So this will give us some function of theta. So in this case, this is just going to be, like if you have some Bernoulli theta process, like the expectation is going to be like theta, right? I think. Yeah, it's going to be theta. And the idea is, well, what, like, we don't, like, again, this is like, we don't know, like, this is what it should be, but we don't know anything about this just theoretically. But we're going to use our actual data, like, we're going to use this data that we got to say, okay, well, because our XIs were actually drawn from this process, hopefully our actual realizations will be good, right? So then we'll actually take and use our realizations. So this actually agrees with with like what we have before. But it's just like it's very simple. It's just, in general though, if you're just going to set all your sample moments, so if you have like k, like if you have k parameters, you're going to like, the idea is basically you have all your moments. So expectation of x squared, all the way to the expectation of xk. And this is basically the idea here is this is like some theoretical. I don't know how to spell theoretical. Like this is like theoretical, like not your sample. This is not your sample, right? This is theoretical. And the idea is, well, if it's theoretical, it doesn't help us because it's just some function of theta. Like, our theta vector. Like, it can't actually help us to compute what these theta should be So instead, we estimate it with the corresponding sample, the empirical. Right? So we then sort of estimate this with our empirical moments. And because we actually have data, we could actually compute this. So this is empirical. This is what we can compute. This is what we could actually compute. And then we set for all I, and the set 1 to k, we equate the expectation of x to the I to 1 over n sum I xi. Well, that's probably a bad notation, some j to the I power. Yeah. So it's just like the idea is like, you know, because our actual data is drawn under this process data, like the empirical should be close to the truth. But again, like we're going to see the expectation. I'll make a video on Fisher's information, and the expectation, the key part is just like, it's talking to it's really important, and it's going to come up in p-value. A lot of this stuff is to make the distinction between the random variable, which is the population. This is about our population, which is theoretical, but we can't observe it. We can't. And our actual realizations, right? So that's why the expectation is nice, is like, it's going to take all the randomness, so all the possible realizations we could get from a distribution, and it's going to just sort of summarize it into one value, like what we typically get. And it's the same argument here, is that we should estimate our parameter theta with like we know what it should be theoretically, and we'll just use our sample approximation. Yeah, so that's a video on these two topics.